By default, standard BGP routers inject the routes they have learned into the routing table, where they inject the destination and the next hop. And we have seen last week that this requires table lookup to be recursive. They can also do more than injection. They can do redistribution, which means that the interior gateway protocol, the routing protocol inside the domain, can propagate the routes that are learned by this. You will advertise that, you will study that in detail in the lab. And what we have seen here last week is that it works only if your interior gateway protocol is able to handle it, which in practice is often not the case because the number of prefixes that are injected may be very large. And second, it is perhaps not desirable to do this because the interior gateway protocol is designed to discover all the prefixes of one domain of modest size, and most of the changes are probably due to exterior routes. But some systems do it, in particular if you use OSPF. But in general, many operators consider that redistribution is harmful. Now, let's assume we have a network where BGP routers do injection only of the routes. So for example, here I'm showing two routers, R6 and R2, that have learned some external route from BGP, either directly from the outside or indirectly via the iBGP mesh. So what would happen is that at R2, for example, or at R6, when R5, R2 learned. Yes, R2 has learned from R6 this route here with destination 18.1/16 and next hop 2222. So injection means R2 will write this entry into the forwarding table. And when a packet comes here from somewhere to this destination, of course we will use recursive table lookup to know how to go to this, but this is an internal prefix for the domain in the middle here, because remember the boundary prefixes, the boundary networks are considered to be internal in both of the networks to which they belong. So that will work. The packet will be sent in the shortest path or whatever attribute is decided for routing inside this domain towards R6, which in this case means it's sent to R1. Question to you, what happens when this packet arrives at R1? A timeout in 5 seconds. The majority says B, but this is incorrect. Because here R1 is running only the interior routing protocol. So R1 is not running BGP, which makes sense. R1 is in the middle of this network. Why would it run BGP? But R1 has, therefore, but because it doesn't run BGP and we do no redistribution, R1 has never heard of this prefix, 18.1. There's no mechanism. It would have heard of it if we had done redistribution, and redistribution is one way to do it, but we've seen it has a high cost. Here, R1 has no way to know what is this prefix. It's never heard of it because the IGP does not get the prefixes like this one. They are not redistributed. Therefore, it cannot forward it. R1 has never heard of it. It's an unknown prefix. The packet is dead, right? So we would send an error message back to the source. Of course, it's a problem. If we do that, it doesn't work. What could we do to solve the problem? Well, one thing that is often done is to run BGP in all routers. So if you run BGP in R1 through the, of course it would be an interior BGP, then R1 will of course discover this, 18.1.16, it will discover it from R6. And with next hop 222, so by injection, R1 will put into its routing table this information. So this is very frequently done Of course, it means that if we do this, we will run BGP even in routers that are not at the boundary of the domain. Here, we would run it at R1. This is often done, and that explains why we have this somehow paradoxical situation where we run BGP in this thing. In essence, we say, in order to carry all the information about the external prefixes, we have two choices. We can redistribute them from the boundary routers into the interior routing protocol, and then the interior routing protocol has to do the mechanics of distributing and computing shortest paths. Or we use BGP for that. And very often that's the second choice that is taken, because BGP is, of course, dimensioned in terms of size of the tables it can handle, is able to handle the very large table sizes here. But that is, of course, at a cost. The cost is that now we will have a larger number of BGP routers in our domain. There are many cases where we can do optimization. If a domain is well structured, if it has a layered structure, then it's possible to optimize. But in theory, that means we need to run BGP everywhere, which means a large size of the IBGP mesh. We will see in a minute that there are optimizations for that. We can use various optimizations to address this problem. There is another solution. Okay, so that was the... there's another solution that perhaps some of you have discovered. We can use MPLS. This is often done in large provider network, like France Telecom does this, as far as I know. MPLS is something that we will discover in 2 weeks when the students who took the research exercise will explain to you how it works. So I don't want to give too many details, but in a nutshell, the minimum we need to understand for that is MPLS is a technique that comes in addition to IP inside a network, where MPLS gives labels to packets, and the labels can be used, for example, to identify virtual LANs. This is what we will discuss in 2 weeks. Or they can be used to identify exit points, for example. A label could identify the exit here. And now, if we use MPLS, then at the routers that run BGP, then we can associate a label that is derived from the BGP information. For example, at R2, we could say, whenever I have a packet that goes to this destination, I associate with it a certain label, and the label is such that, of course, we need that R1 is an MPLS router, so it's able to forward packet based on the label, and this label, through the forwarding rules of MPLS, that we'll discover a bit later, will reach R6. So in some sense, we create an overlay that instead of carrying all the information of all the external prefixes, we carry only the information of the exit points here. So that is very, very superficially. There are lots of issues that need to be solved. In particular, everything is dynamic. So BGP will change its mind. Sometimes this prefix will be reachable here, but sometimes it will be reachable there. So we need to have a mechanism to change those label tables, which is typically more work. Voilà, that's the basics of BGP and how it's able to gain information about external prefixes and put that information into the local network to be able to run optimally. Now, because BGP is one of the main BGP stuff is to do policy routing, and doing policy routing with rules is a bit contorted. Ideally, you would like to be able to write an expert system to say, I want this, I don't want that, but BGP uses the decision process, essentially. So the way that has been found to make this possible is to add more and more attributes. We have seen a number of attributes that are associated with BGP routes. There is the destination prefix that defines the route, the AS path, and the next hop. That's the minimum we need. In addition, we can give more attributes that will help the decision process. One of them, for example, is called the local preference, which is a priority field where high means better. For example, a typical case could be a network that has several neighbors and prefers one. So perhaps you want to go here because that's your service provider, for example. But since you don't trust your service provider entirely, you still want a backup path in case things go wrong here. So you might have a different connection to another system that perhaps costs you more or is less reliable. And you can signal inside your domain that you prefer this one. You do that by putting this priority field, local pref, to a higher value to all the announcements that will be received on those BGP peerings. Here is an example. Here I have AS4 that has two connections to the outside world to go towards AS1 via AS2 and AS3. Connection to AS2 is a good connection, and the connection to AS2 with this shadow key line is not so good. So it would prefer to send traffic here, but you keep this one as a backup. Then AS4 will set the local pref to 100 to all routes received from AS3. So for example, when R1 receives the route, this route AS2, AS1, 10.1, so when it receives a route via this way, it sets its local pref to 50. Right? So R2 via the iBGP, R2 will receive similar here and will set its local pref to 100. This is done by the routers that are running eBGP. And now if we run BGP inside the mesh, and eventually R3 exports something to AS5, what will R3 announce? Timeout in 5 seconds. Oops. And the correct answer is B. Indirectly, this is a question on what R3 has selected as best route, because we know that one of the rules of BGP is that you can announce nothing, or if you announce something, it has to be the best route that you chose. So here, R3 will receive from R2 and R1, each of them will receive 2 routes, but this one will have a local pref that is smaller, so it will not take it, so it will announce the route, which is this one, that has been received from AS3 and had a local pref value that is larger. Now the local pref is only inside the AS4, so it is not exported, as you can see here. So the local preference is a field that you put inside your domain to orientate your choice, but there's no point giving it to another domain. Another domain will do their own choices, so local pref is not exported over eBGP, typically. Which means in particular that all traffic from AS5 will go this way, at least as long as this link works. Now, if this link fails, we still have the backup link and that will be able to do the job. I skipped some of the things, so there's more than 100 attributes in BGP. We won't see all of them, but we'll see some of the most frequently found. MED, multi-exit discriminator, is a kind of preference that is also given, that is also used, but this one is exported, is used by eBGP. MED is a preference, but as you can see, that's typical of TCP-IP stuff. There's no useful convention that you can adhere to once for all. So here, best is low, whereas local pref is the opposite. And it's typically meant to signal preference that a customer has when it has multiple links. For example, ASY could be the Tesla company that has links and charging stations and cars everywhere in the world, and connects to a provider that is, for example, AT&T, and therefore you're connected at several points. And here you might want to say that I want local traffic to be local as much as possible. So if you remember we saw last week that in a case like this, R3 might well export everything it knows of, which are those 2 prefixes, and then the rules will be such that we do hot potato routing here. Now, if you want to change those rules, then you can signal to X that you have a preference for this prefix, 10.1, to go here. I export 10.1 by R3, also exported by R4. But when R4 exports 10.1, it puts a med of 50, which means less preferred. So this is signaling, the intention is to signal to X that if I want to go to this destination, I have two ways, two next hops, 111 and 222, and the one that Y prefers is the one with the lowest, which is this one. Which means that I would like that you carry the traffic for me. I would like to do the opposite of hot potato routing. So we want, Y wants that if there is some traffic coming from this side of the world going to 10.1, it should go inside X to the next hop 111. So we should prefer this interface. This is signaled by this field here. Now, it's a field that is passed at an interface, so between two domains. So when you receive something from someone else, you're never obliged to take it. There is an import policy. So here I am assuming that the import policy at X accepts that Y puts a med, which is typically the case if X is a service provider to Y. If X and Y would be peer, perhaps Y would like to do the same trick, but the policy of X would typically say ignore med, or whatever X wants to do. Yet another quiz to see how med works. Time out in 5 seconds. What is the correct answer? So we are at R1, right? R1 has received two routes, so this one and this one, and to 10.216. Now, this route here has a med of 50. This route has a med of 10. Now, the question is, in which order does the decision process test the different things? Because there's another thing here. That is, R1 has received the route from iBGP, from R2, and from eBGP. We know eBGP is preferred, but the med is tested before E versus iBGP, because that's the purpose of the med. So the correct answer is the route via R3, which is not the majority. Whoops. Which is not the majority vote. It would be the route via R2 if there would be no med, but the med is tested before E by GP here in the decision process. Right? So you see that the med attribute is one that is really deeply entrenched in BGP because it's encoded in the decision process. Now, if this router crashes, let's analyze what would happen. R1 would detect the loss somehow by the keep alive, the heartbeat mechanism, and would clears all the routes that were here learned from R3. All those routes were stored in the in database, the RIB in, and R1 has other routes that it had learned from R2. R2 will also clear the area. R1, before doing that, R1 will, of course, before informing R2, R1 will pick another route to those two prefixes, the one it had learned from R2, which is stored in the RIB in. So it will pick now this route because it's the best, being the only one. And because R1 has changed its route to, for example, this prefix, 10.1 and 10.2, it will inform R2 of the suppression. And R2 will also therefore change its route and send all traffic here. So we see that in a case like this, all traffic from X to Y will flow through this link, which is illustrating the purpose of that. We want to have redundancy. We want to have a preferred choice and use the non-preferred choice only in case of backup. So let me skip this. There's a number of other fields that I'll let you discover offline. There are many other bells and whistles. One of them in particular is avoiding too many iterations. One of the beauties of BGP is that it advertises only the deltas, only the changes in its preferred routes, in its best routes, and the one that can be exported. However, there's a downside to it. If occasionally you have a router that has instabilities, it has intermittent faults, so a typical crash fault in a well-behaved online service would result in reboot. So a process crashes, then it's automatically rebooted. So if the BGP-D process crashes, it will be automatically rebooted. If it's a transient error that was due to an alpha array corrupting one bit somewhere in the memory that was not caught by error correction codes, that's fine. That's a rare event. If it's a bug or malicious software, when you reboot, the crash will come up again. Or if in the best case, it will come up again later, because if it was a crash due to some kind of software aging, that the BGP process is not properly cleaning some of the thing it uses, then perhaps after 20 days of running, it will crash. That's fine, no problem. But if it's malicious software or a serious bug that crashes it very quickly, then it will come up for a few seconds, crash, and go down. What will happen in a case like this? When BGP crashes, when this BGP process crashes, all the neighbors will discover new routes and will send withdraw and update messages all around. Then this new process will come up again, so they will again change all the things that they had undone. They will redo again and again and again. So we will have an avalanche of messages that is like a denial of service attack. So that has happened, and in order to avoid that, we have what is called a dampening mechanism, where when you withdraw a route, you keep it again. Normally when you withdraw a route, you delete it from your rib in. But in fact, you will not delete it, but you associate some aging mechanism to this route so that you can test whether it's coming up again very soon, so that you can detect if a route is oscillating. It's called a flapping route. If the route comes up, comes up and goes away, if it does that repeatedly, you can detect this because you have kept it in memory here. More precisely, you associate a penalty to the route, and when the route is suppressed, the penalty increases. So if it's suppressed one, fine. But if it's suppressed several times, then the penalty is above the suppressed limit, and then this route is never considered. It is as if it was totally absent. So even if you receive an update for this route, you will not use it. And then you have, like any good learning systems, you need some aging. So the weight here decays exponentially, so that if nothing bad happens, so if this route has been suppressed sequentially a very large number of times, then it's suppressed. But if for some large amount of time it was reinstalled by your neighbors, so you receive an update, but it was not suppressed during all that time, then you reuse it again. So that means the router that was causing the problems around has been killed or fixed. Here. Another trick that is often used is that of private AS numbers. It can be used first when we're testing things, like we do in the lab. If we would not be using virtual machines, then we would use private numbers to make sure nothing leaks. But it can also be used for a number of tricks. For example, here, in a case like I mentioned that EPFL is connected to switch, and switch is the only provider that EPFL connects to. Therefore, EPFL doesn't need an AS number, which is true because all traffic to EPFL goes via switch. However, if you would like to use some of the benefits of BGP, for example, one of the benefits of BGP we have seen is the ability to have multiple access links to the same provider, be able to say which one you want to use where, and use as backup the non-preferred one. So you could imagine this is EPFL, this is switch, and this is Lausanne, and this is Neuchâtel, for example. Then you would not like that all the traffic between Lausanne and Neuchâtel goes via the internal EPFL links, but you would like that switch carries that for us. Then you can do it if you are a true BGP, an AS with a number, so an autonomous routing domain that has a number. And one way to do it is to use a private number. So you agree with switch what is your private number, and you use BGP between the provider and the client as you would do if you would have a normal AS number. But it's a bit like NATing at the IP layer. The provider will replace your private AS number by its own AS number for the rest of the world. So that by translating it. So for the rest of the world, this client is invisible. So that's one use of private AS numbers. Yet another small quiz. Assume we have the following messages that are being routes that are being exported by BGP. So this one has the number 100, and it exports the prefix 2.1 with the path 100, 100, 100, 100. You could think of it as a bug because there's a loop. But BGP says it's not a loop. If you see the same number several times contiguously, it's a bit weird, but this is all done by software people, so we are all weird. So they accept this. So assume we do this. Which way will follows packet from Z, where is Z, here, to 211, to something that is here. Time out in 5 seconds. And the correct answer is B. Because the first rule that is tested, one of the first rules that's tested is the length of the AS path. So this is a long AS path. This is a shorter one. Therefore, this one will be preferred. It's a bit funny way of testing, of replacing the MED. So a poor man's MED consists in doing that. You will see that once in a while. If you look into databases to look at AS paths, you will see that kind of thing. It's another way to signal, a bad way in my opinion, but it's another way to signal that this path is not preferred. Now you speak up to do the polls, but you can also use it to put messages. And I see that somebody's complaining about the result of the previous slide, of the previous quiz. So let's go back here. Not this one. R1 has 2 routes, so we're calling 10.2. This one here, and obviously, yes, this is correct. This is you were right, and I was wrong. So we will have minus 1/3 for my quiz here. So thank you for pointing out. Yes, of course, this is the correct answer, not this one. So this smaller MED is preferred, so this guy will receive the smaller MED and will go to R2. Sorry for this confusion. Another use of private AS number is to reduce the complexity of the internal BGP mesh. So if you have a very large network with lots of BGP routers, and we have seen that you may have lots of BGP routers because you use injection only and no redistribution, in which case you need to have BGP everywhere. You use BGP in all routers to transport the external prefixes. Then you can structure your network into subdomains and give an AS number to each of the domains, which you can use as a private number. And then you can run BGP between the subdomains as if they would be independent domains. So you can use, so this is perhaps a very simple example where there's a single point of peering between two subdomains. Typically you want more than one, but this will have the effect of having a hierarchy inside my domain. And if it's done well, the crux when doing this is to make sure you have enough, you don't have single points of failures, of course, here. In the drawing that's given here, those BGP routers are single points of failures. If this one fails, then we have lost BGP connectivity between this part and that part. So obviously you do it with more than one point of communication between domains. So this is one of the solutions. It's called a confederation of BGP domains, one of the methods that is used practically when you have large domains. Another method is called a route reflector. A route reflector is essentially the same, but is inside the IBGP protocol. Right. So I'm not sure why we have both, but at least functionally they are performing exactly the same thing. The route reflector or the confederations, we will not exercise them in the lab because they make sense only when we have large domains. Something you often see if you search for BGP information is the concept of route servers. So route servers are a different thing. It is used to avoid what is called sometimes the eBGP mesh. What is that stuff? In principle, there is no eBGP mesh because you interconnect to a neighbor network. But very often, interconnections are not by having point-to-point links between providers, but at so-called interconnection points. An interconnection point, also called an internet inter-exchange point, is a place, usually in the basement of a building, where all providers have access and interconnect to each other. So it's a place where there are huge multi-gigabit per second switches, and every provider provides a BGP router or rents a slice of a machine that provides a BGP router and connects to a large number of other providers. Now, if you are in a place where there are 200 providers, then you connect to 200 different other neighbors, if you connect to all of them, which is often the case. And then you have, again, a BGP mesh inside this inter-exchange point. So this is showing 4 domains that interconnect at the same point. So this is avoided by having a server that you can put in the middle that acts as a mailbox. Instead of running BGP between every possible pairs, you run a special version of, you run BGP between what is called a route server that then, so when you send an update here, then this update is rebroadcast to all other BGP routers. And those route servers are very convenient because typically, if this is allowed, this is a place where you can observe all the BGP traffic. And by observing all the BGP traffic, you can learn also some information about the topology of the internet. So all the information, in fact, we have about the topology of the internet comes from information learned in those so-called route servers. Yes?
This centralized server, the purpose of having some redundancy in the BGP speed, because now the server is somehow disconnected, everyone goes.
Excellent, a very good point. Of course, whenever you do something like this, you're introducing a single point of failure, like we were doing in the confederations or in the route reflectors. So you need a mechanism to have some fault tolerance, which obviously you have. So, we're not discussing that in detail, that would be a topic of its own, but you can easily imagine what such a mechanism would be. What would you do? Well, there's no magic. If you want to have some fault tolerance, you need to have replication. So you will have more than one of those machines. So you would have a number of them. And the simplest way, which is the one often deployed by Cisco, for example, is to have, so you have one that's the primary that's working, you have a second one and perhaps a third one that are backups, and you have a fault detection mechanism between the backup and the primary and secondary, so that a keep alive mechanism, typically. And whenever one of the backups detects that the primary is down, then it will take over the function of the primary, which can be done, for example, if they use the same IP addresses. Then if you manipulate the forwarding table in the system such that all traffic that goes here also goes to the backup. But there is, of course, some works to do that in detail. But this is done typically whenever you have a unique service somewhere, you typically have, in the simplest case, a backup. BGP, like much of the internet, paradoxically, was designed without security in mind, whereas it's the most important protocol in the internet, because that's the one that really dictates whether we're able to reach some destinations. And we've seen that there might be reliability problems, but because the internet is so immensely meshed, so many providers connect to many, many providers, so if we lose some peerings, typically there is always a very large number of backup paths, and one of them will be used by BGP. But security is another story. For example, assume I have here, I'll take the same case as before, but this ISP, assume is malicious. Right? Now you say, why would an ISP be malicious? I mean, those are people who are doing regular business. I mean, you don't expect Swisscom to be malicious. Well, there are multiple answers to that. I mean, first, inside Swisscom, there could be a malicious employee, disgrudged employee, who decides to revenge because he's fired in 3 months and a 3 months notice. So during the last 3 months, he will cause damage. That's one. And many of the malicious problems come from insiders. But unfortunately, in the world, there are also malicious networks, right? There has been attacks, for example, from Russia on Estonia. There has been attacks from Pakistan on some websites. So those things have happened in the past, right? So assume this guy is malicious, and assume this guy, us here, are injected this route, and this is MIT. They're jealous of EPFL, so they want to discover all the things we're doing here. So one way they could do, for example, is to inject this prefix here. Right. So of course that's completely illegal. So they say, I have this prefix in my local domain. I'm locally attached with a local next hop here. What will happen? So let's time out. So most of you say B, so some fraction of traffic to EPFL will go to ISP3. It's hard to know in reality because here we have, it has to do with aggregation. So EPFL has injected a route on 15 bits, a prefix of 15 bits, and this guy is injected a route which is in fact 2 sub-prefixes of this one, right? He's injected those 2. If this guy does aggregation, for example, then it will have 2 prefixes, 2 routes to this one here or one there, and then it depends on the local decisions. So A, B might be correct. Now, if all those guys around here don't do aggregation, which is typically the case, I mean, aggregation is expected to be done here, perhaps there, but not by this one here. So all things that will not aggregate, they will have 3 routes. This one, and that one, right? And which one will they prefer? Well, we don't know, but if those are 3 different routes, so the question is not prefer one versus the other. If they are all accepted, if they are not filtered out, if a router here has those 3 routes, any packet to one of those destinations will have, by longest prefix match, will match one of the 2 here. So we'll go towards the route done by ISP3 here. So all routers in all domains that have not aggregated those 2 into one here will send all traffic to ISP3. So that's and most likely most domains will not aggregate. So the answer is B, but a very large fraction of B, a very large fraction will go to ISP3. So this is one attack, very easy to do. As you see, you don't need to be a cryptography expert to do that. It has happened. It has happened. There was by error or malice some networks of some countries, for example, advertised some sub-prefixes of Google, of YouTube, and they attracted all traffic of YouTube, where of course they killed it because they didn't want some people to have access to some content. Voilà, we do a break and we resume at 1:15. So we see that it's very easy to abuse BGP by sending false announcements. Those things happen. Typically they are detected, and after they are detected, for example, if ISP3 is isolated at performing this, then what happened when such cases were detected, all other ISPs in the world detect to ban ISP3, so any advertisement that is coming from here by all the neighbors is simply thrown away, and then they call someone at ISP3 for having them fix the problem, which is very manual and takes a lot of time and works as long as such things are rare isolated events. The Internet Engineering Task Force is working on what is called BGP-Sec, a security addition to BGP. But there is a lot of resistance to deploy BGP-Sec. We can make the difference between two different levels of security. The first one that is obviously missing is authentication of the AS number and the IP address blocks. So in the attack that was shown before, this guy is saying this block belongs to me. Right? But that's easy to know that it's not true because the IP blocks are allocated by one central entity. I said there is no central management of the internet. It is true. Nobody runs the internet, but someone runs the numbers that are allocated in the internet. In particular, the IP address is called IANA, and this entity knows who has what. So the company that has this AS number doesn't have this block. So that is known to IANA. So you can call someone at IANA if you have a doubt, or better, you can authenticate the AS number and the IP addresses. What you need is a system of certificates like we have when we do e-banking, for example. You need a root of trust. So you need companies that are trusted by everyone that delivers the top-level certificates. And those top-level certificates are used to sign the AS numbers and the blocks given by the AS numbers. So what you need is a public key infrastructure, and there is one RPKI, which R stands for routing. So it's the routing public key infrastructure. So it is a set of certificates and a chain of trust rooted at IANA that authenticates all the AS numbers and IP addresses and also who is supposed to own them. So if we have this, the previous attack would not be possible, at least if everybody verifies all the announcements. That means we would have more attributes in the BGP routes, not only that means that you need simply to verify when you receive AS numbers and IP addresses by additional fields that are given in the routes, whether they come from the legitimate sources. But of course, that would solve only some problem of relatively simple attacks like this one. You can imagine very easily, and there's a few papers that describe, if you do a search on IEEE Explore, you'll find a few papers, or ACM, you'll find a number of papers that describe BGP attacks. What you can do is not just originate a false route, but you can also forge announcements. I mean, BGP says you must advertise only your best route, But you do that if you're not bogus, if you're not malicious. If you're malicious, you can export something else. So you could pretend that the path that you've received are completely wrong. So you could send a path here that is completely wrong. So you could say to ISP1 that everybody here wants the traffic to go through me by forging an announcement that you have never received here. One solution to that is called BGP-SEC, where with BGP-SEC we keep here authenticating the AS number and the IP address blocks, but we digitally sign every addition, every change we do to a message. So if I receive a route, I keep it as my best route and I forward it to you, I will do one change. Which change? Well, I will add my AS number. So I give to you a new route, which is the one I had received, plus the AS number. So the idea is that any addition should be signed and authenticated. So the route I have received was signed and authenticated. I keep this signature. Then I modify it, and I have to sign the modification. Of course, this is recursive. The route I have received has been constructed in this way. That means it contains a number of AS paths. Every AS that has been added has been signed. So it's like an onion. I have to sign and verify everything recursively. That's the principle of BGP-SEC. If you do this, that will not guarantee that there's no fraud, but that will guarantee that any fraud has been done by somebody who signed it. So it's really, it will be easy to pinpoint where the problem comes from. So you can do this verification, again, if you have a chain of trust, if you have all the necessary certificates and public key cryptography mechanisms to verify this. I said there's a lot of resistance, because if you do that, you can imagine the processing time it takes not to process a router. So if you receive an update, and whenever the path is, for example, 10 AS path, then you need to do 10 signature verification to accept it. So signature verification, if you use ECDSA with pre-computed token, can be made fast, but still we're talking of the order of 1 or several milliseconds per signature on a standard modern processor. So that means if you have an AS path that has 10 entities, it means 10 to 20 milliseconds for verifying the signature. Which of course is good business for those who sell BGP routers. That means a BGP router becomes all of a sudden an extremely high power processing machine with lots and lots of cores and lots of optimization to do this cryptography, perhaps in the hardware instead of, like I mentioned, the numbers I mentioned are for cryptography done in software. So that is good news for router vendors, much less for those who buy the routers. So this is why there is some resistance, but there's no doubt it will come, because the fragility is too large and the exposure is too important, so that we will need those solutions. Yes? How frequent are BGP messages?
Because if they're not so frequent, you said that how many modifications
I don't know, to be honest. I don't know how frequent they are, but I can imagine there are periods of time, critical periods of time, where there are many. Typically when something was down somewhere, I mean, you've lost a router somewhere, so all routes are changed from west to east, for example, then you will have a very large number of routing updates. And because the density of the graph of interconnection is very large, so we have lots of neighbors everywhere. So whenever there's one change here, everybody is affected here. So I don't know the numbers, but you can imagine they are large. Remember, the size of the number of prefixes is typically order of 500,000. Right? So even if you have not so frequent, but a change of a block of tens of thousands might still be an issue. So if you read the literature, it is an issue for those that are running BGP today. They say, we're not able to deploy BGP-SEC today. It is, so the numbers are such that it's not possible today. But they will be possible tomorrow. When we talked to companies 5 to 10 years ago, They were saying that doing encryption and authentication on all lines at gigabits per second is too expensive. You don't want to do it. Now everybody does it. So similar things are likely to happen here. A few examples. This is the interconnection, for example, of the switch network. That's the physical interconnection. I mentioned that there are inter-exchange points. The very famous ones are May West and May East in the US, that are two exchanges where all the main carriers of the world interconnect. If you bomb them, you will be losing. If you bomb both, the internet will be in serious trouble. In Switzerland, there is also such things. For example, in Zurich, there is this place where you can go if you want to start an ISP business tomorrow. It's a good idea to peer there. So you rent some space in one of the racks, and you will do your BGP peering to all the people who do it there. Our provider is Switch, so you can search all the details about Switch. You see its AS number, 559. And this is the world switch from EPFL, or more precisely from Switch. Those are all the AS numbers from Switch, because EPFL is inside Switch for the rest of the world. And you see that Switch itself, I took this snapshot 2 years ago, I guess there is more now, is connected to a very large number of other ASs that themselves are connected to large numbers, etc. And if you do that at larger time scale, you will see things like this here. You mentioned what are the number of announced prefixes. So a historical graph. When BGP started, which was at that time, we had a few thousand prefixes, and now we are at 500,000 for IPv4, and for IPv6 we are at 20,000. So that's the major reason for going to IPv6, is to go from this to that. Now the bad news is, on the way to IPv6, we need to have both. So we are worse than before. Voilà, that's for BGP, at least for the theory part. The rest you'll be discovering in the lab.